In this module, we discuss phase transitions in the standard state. When examining two phases of the same substance in its standard state, the transition between them occurs at the standard pressure of 1 bar. Essentially, as we move from lower to higher temperatures, we cross coexistence curves at constant pressure. This process is what we commonly understand as phase transitions. Now, if the triple point of a substance is positioned at a pressure less than 1 bar, the substance transitions through the three conventional phases, starting from solid, then to liquid, and finally to gas. However, if the triple point's pressure is above 1 bar, the substance directly transitions from solid to gas, bypassing the liquid phase. What determines which phase, solid, liquid, or gas, is most stable at a given temperature, when the pressure remains constant? Fundamentally, it's all about the chemical potential and entropy. In this figure, the chemical potential μ is plotted against temperature for the solid, liquid, and gas phases at a constant pressure. These dependencies are reasonably approximated as straight lines. We can argue that, in principle, at any given temperature, any phase of the substance potentially exists, but the phase with the lowest chemical potential is the most stable one. Importantly, the slope of these lines is the negative of the molar entropy for each phase. Higher entropy corresponds to a steeper slope. It is also known from experience that as a solid melts to form a liquid and as a liquid vaporizes to form a gas, heat is absorbed. Both processes are endothermic with delta H more than 0. Therefore, the entropy increases in a stepwise fashion in these processes. And the entropy of the three phases follows this order. The entropy of the solid is the lowest, the entropy of the liquid is intermediate, and the entropy of the gas is the highest. Thus, the negative slope of the solid phase is less steep than that of the liquid, and the slope for the liquid is less than that of the gas. Purely geometrically, if the temperature is sufficiently low, the line of chemical potential for the solid goes below two other lines, and the solid phase becomes the most stable one. Now, we know that the temperature has a lower limit, but indeed almost all substances in their standard state become solids when the temperature approaches 0 Kelvin. The only exception is again helium, which remains liquid at around 0 Kelvin at the pressure of 1 bar. Then, as we increase the temperature, the line representing the chemical potential of the liquid eventually falls below the line for the solid due to its steeper negative slope. Their intersection is the point where the chemical potential of the solid phase equals the chemical potential of the liquid phase. It represents a thermodynamic equilibrium between two coexisting phases at a certain temperature. Here it is the melting point, Tm. If the temperature moves slightly above Tm, the solid melts completely if it is kinetically feasible, as the liquid phase has a somewhat lower chemical potential. Similarly, the slope of the line for the gas is steeper than the one for the liquid. If we raise the temperature enough, the line for the gas, which is steeper, will fall below the line for the liquid. The intersection of lines for the liquid and gas represents the equilibrium between these two phases at the temperature known as the boiling point Tb. At temperatures above the boiling point, gas is the thermodynamically most stable phase of the substance. If we consider these phase equilibria at the standard pressure, we talk about standard melting and boiling points. It can also happen that the line for the liquid is higher than the intersection point of the lines for the solid and gas, meaning that the liquid phase does not exist in the standard state. Having understood how temperature affects the stability of different phases of a substance, let's take a look at how the temperature of a substance changes as we add heat at constant pressure. It is shown schematically in this figure. Here, the heat flowing into the system at constant pressure is denoted by Qp. Each section represents a specific phase or transition in the heating process of a substance. We start from the substance being in the solid phase. As we warm it up by providing heat, the temperature of the solid rises in an approximately linear fashion. At this stage, all added heat is converted into a temperature increase as determined by the heat capacity at constant pressure. Once we have reached the melting point of the substance Tm, the temperature stops increasing as we add more heat. This constant temperature is a feature of phase transitions. During this period, the heat supplied is used to change the phase of the substance rather than increasing its temperature. Specifically, here, the heat taken up at this stage is the enthalpy of fusion, representing the energy required to transform the solid into a liquid at a constant temperature. The temperature remains unchanged until all solid material melts, or at least this is how it should be in an ideal reversible thermodynamic process. Once the entire substance has melted, it is fully in the liquid state. The temperature again rises steadily with the heat added, similar to the earlier stage but with a different heat capacity. This continues until the temperature reaches the boiling point of the substance, Tb. Similar to the melting stage, the liquid begins to vaporize while the temperature remains constant. The vaporization requires an amount of heat known as the enthalpy of vaporization. Once the entire substance has vaporized, we obtain a gas phase, and any additional heat will further raise its temperature. In conclusion, the temperature of a substance doesn't rise uniformly with heat addition. Instead, we observe periods of steady temperature rise corresponding to individual phases, interrupted by plateaus at phase transition temperatures where phase transition consumes the heat. The regions of constant temperature showcase the thermodynamic necessity for phase transition to occur without any change in temperature. Any deviations from these plateaus, and we are looking at non-thermodynamic irreversible processes. Furthermore, this example illustrates that, in contrast to some common understandings and figures of speech, heat is not equivalent to temperature and does not even correlate with it.